Welcome to the lecture on biodiesel. We have a short guest lecturer as well, so we'll get started.
Okay. Biodiesel is made from oils and renewable plants and/or animal feedstocks. Biodiesel is made through a chemical reaction producing a fuel with properties similar to diesel. Biodiesel is a fuel which can run in any diesel engine without modifications.
All right, so what is biodiesel? So the technical definition is it's a fuel comprised of monoalkyls esters of long chain fatty acids derived from vegetable oils or animal fats. And that would be designated as B100 and then meets the requirements. So there's a standard, the ASTM D6751 standard. So again, it has to meet those standards in order to be called a biodiesel fuel. So again, biodiesel has a lower emissions and a higher flash point. So again, it's biodegradable, essentially non-toxic. When you burn it, it actually kind of smells like French fries, depending on what you make it with at the tailpipe there. But it's basically, again, as we said, it's these it's chemically bonded molecules, and they're monoesters produced from triglyceride esters. So again, if you think about vegetable oil being a glycerin with fatty acids, and then we add alcohol to it, we add methanol. And then what happens is the alcohol and the fatty acids connect and form biodiesel, and you're left with a glycerin byproduct. Okay, so this is essentially what biodiesel is. So again, we can do just like you can have ethanol being E10 or E100 or E85, the same thing for biodiesel. So you can have pure biodiesel, which is B100, or it can be blended with petrodiesel to be like a B20. Again, this idea is not new. Actually, Rudolf Diesel actually used peanut oil when he developed his diesel engine. So this is not anything that's new. And again, with biodiesel, with diesel engines, there's little or no engine modifications that need to happen. So we can use it with our existing fuel distribution system. And again, it is something that's available now. So again, when we're talking about biodiesel, specifically, again, if we're talking about the plant cell, it's used in the formations of these fatty acids and the triglycerides. So this is what we're interested in. So the individual fatty acids are generated within the chloroplast, and then they're shuttled to the endoplasmic reticulum, and then they're combined with basically three G3Ps with those phosphates to create this more stable triglyceride that is, again, that fatty acid synthesis. So again, it's a combination of the triglycerides and a monohydroxyl acid. So usually methanol, but it could be ethanol, but it's any monohydroxide acid. So again, here is our glycerol connected to our fatty acids. And then what we have here is this triglyceride is a combination of made from a combination of glycerol and three fatty acids to form that triglyceride molecule. So once we have our triglyceride, we're going to add it with the methanol again, and that's going to form our biodiesel, which here is our formula here, and our glycerin that's left over. So again, this R1, R2, and R3 are just fatty acid alkyl groups. They could be different, they could be the same, and it really depends on the type of oil that we have on what these chains look like. But then the fatty acids involved turn the final property of the biodiesel in terms of the octane number, the cysteine number, the cold flow properties or flash points, etc. So again, the first step, triglyceride, excuse me, is turned into a diglyceride, and then methanol, methodox minus the Na minus sodium, joins a freed fatty acid to make this biodiesel, and then the sodium, which is again a catalyst, joins OH from water from this methodox formation to make NaOH, and the H then joins the other diglyceride. So again, we have our triglycerides, our methodox plus water, and then we get our diglycerides, our biodiesel, and our NaOH, which is our catalyst, which can be used again. So if we think about the whole step, here's a simplistic approach to how it can be. So if we do you don't have to use waste veggie oil. It can be sunflower seed oil, palm oil. It can be various oil. But basically, once you have the oil, you're going to heat it to about 120. You're going to check the titration level, and the titration level basically is making sure that you're putting the right amount of catalyst in. And so you make sure you have that correct. Then you mix the lye, which is our catalyst, with methanol in a separate container. And then we're going to pour the solution into our processor, and we react by mixing the methanol, the lye, which is our catalyst, and our oil. We allow the oil to separate, so the glycerin comes down and the unwashed biodiesel is there at the top. And then we're going to remove that glycerin layer. And then once we have the removed glycerin layer, we're going to wash the biodiesel. So then again, we have water and biodiesel, and then we're going to again get that water out. And then our washed biodiesel is going to dry, and then we're going to transport, and it's ready to go. So you can actually do a wet wash or dry wash. So again, the same thing. We have our catalyst, our triglyceride feedstock, our methanol. Again, with the transesterification process, which is the mixing of these three together, our glycerol comes out, and then we actually can do a dry cleaning process rather than a wet cleaning to get the pure biodiesel. So there's different ways to do that kind of cleaning process. But if we think about our inputs and our outputs, alcohol being about 12%, the catalyst being about 1%, our oil, whatever it is about 87%. And then what comes out is there is some alcohol that can be recovered. Not all processes do recover that alcohol, but at about 4%, about a third of it could be recovered. And then we have some glycerin, which is about 9% fertilizer, and then our methyl esters, which are our biodiesel, is about 86% of what comes out. So in the US, soybeans is currently about 90% of our market, but we also have waste greases, edibles, and inedible tallows, cottonseed, sunflowers, and canola and rapeseed. But in Europe, their majority of their biodiesel is made from palm oil. So if we look at our gallons by region, if we look at our biodiesel production, again, we have some biodiesel being in the Northeast, more being in the kind of the middle states, and then most of our biodiesel is coming from the other states. But again, if we look at the billions of gallons per year, we've grown from 2019 to about 2.5 billion gallons per year. If we look at that difference with the so again, still the majority is coming from still the middle of the country, excuse me. If we look at that compared to ethanol, where again, the majority of our ethanol is also coming from the middle of the country. But again, we're at more of that 16 gallon fresh threshold in terms of ethanol, in terms of billion of gallons per year, which why biodiesel, we're about at 2.5. So 2.5 to 16. So it is a significant portion of our total biofuel market, but it's much less than our ethanol component. So if we look at what we can get, so when we look at the biodiesel production, if we're not using waste oil, if we're using it from seeds, then we have to look at what's our yield, our seed per acre. So how many seeds do we get per acre? And so again, you can see for corn, we get quite a few seeds per acre, less with cotton, with rice, for example, peanuts, pretty high with coconut, and very high seeds per acre with palm oil. And then from those seeds, how much of those seeds actually translate into biodiesel. And so we can see, you know, with corn and soybeans actually kind of being at the lower end, soybeans being kind of middle at 50, around 48, and then much higher with sunflower, rapeseed, peanut, and then finally the palm oil and the coconut is much, much higher in terms of the biodiesel gallon, not only because they have higher yields of seeds per acre, but more importantly, those seeds have very high triglyceride contents. And so if we look at the energy input and output, this is from your reading. So if we look at the input energy, if we look at the input energy for our palm oil, you can see that the input energy is about the same, a little bit less for palm oil compared to rapeseed and soybeans. And then if we look at the output, though, you can see that the palm oil output is much greater than the rapeseed and soybean output. So even though our input is pretty consistent, we just get a lot more. So we just get a lot more output energy for these inputs. And again, on this side, though, we have our production cost. And you can see that, again, our production cost is much lower for the palm oil. So not only are we getting more output biodiesel from, but we're from from our input that we have here, but our also cost per ton of biodiesel production is much lower. And again, that's because we're able to get so much more oil from the same amount of seeds. So we have a lower cost and a higher output. So if we look at the inputs, the feedstock inputs for biodiesel in the US, the EU, and the world, you can see that again, most of ours is from soybeans. And again, we have our yellow grease being about 13%, our canola and corn being a little less. Again, some of this is the output from ethanol production. They're able to separate some of the oils out and do it there. And then animal fats are about 10%. So if we look at, again, from the animal fat rearings and the yellow grease, some of these are waste products that aren't necessarily used, while actual corn like production plants is the rapeseed corn and the soybeans. But again, some of these corn are waste. So what we actually plant is more this rapeseed and soybeans. If we look at Europe, you can see Europe again has 15% palm oil. We don't really have much. They have again their waste grease, their animal fats, and their soybean, but they have a much higher percent of the rapeseed. And if we look at the world, again, the rapeseed being the most, followed by the soybeans and the palm oil. So what biodiesel is not, so it's not a little bit of vegetable oil blended in with petro. So again, we have to go through that transesterification process. You should know that word, transesterification, where we add the biodiesel to the, add the methanol, excuse me, and we actually have a catalyst and we have a reaction that takes place, that reaction being transesterification. So it's not just vegetable oil. And you can't modify a vehicle. You can modify a vehicle to accept straight vegetable oil or waste vegetable oil, but that is not, again, biodiesel. And it's not ethanol. It won't work in a petrol engine. You can only use this in a diesel engine. So again, if you look at waste vegetable oil conversion, you can use vegetable oil in a diesel, kind of like put the oil in, but usually that has to stop and start on petro or biodiesel. And then you have to have some sort of heater, and then you switch over to vegetable oil at a high temperature. So again, it is different than running a car on vegetable oil, the peanut oil, for example, that Rudolph used to do, because we have to do that transesterification process to get it to biodiesel to be able to run continuously without a stop or start on petrol. So we now have it as a commercial process and a continuous reaction. So again, we do this at large scales here in the U.S. But again, the quantity of the feedstock you need for that constant input is high. So we usually have this in places where we have high soybean production, or we know we're going to have a continuous input of waste oil. We have home brewers that do it. So you can make it out of an old water heater, many different setups, from simple buckets to more complex operations. Again, we do need this kind of like cone shaped output, because again, we're going to take out the glycerin. If we're water washing, you're going to have something like this to take out the water as well. And so often you'll use these types of processes. So if you think about doing kind of the home brew or even larger brew with biodiesel, you again think about the entity formation. You'll have some sort of LLC that's doing, is it a co-op? Is it a owner protected? What are the limits in terms of transportation? Where are you getting your methanol from? Where are you getting your used fry oil? And where are you getting your diesel? Again, especially with methanol, it's something that has to be acquired, and there's certain limits in how far you can transport it, and if you can transport it over state lines without different permits. There are also storage limits. Again, methanol is flammable, and so there's storage limits both for the methanol, the used fryer oil, as well as biodiesel, if that's what you're making it from. So again, you would have to have fire marshal notifications, material handling notifications, and safety procedures in place. If you're doing it from oilseed, again, you need to look at, what chart is best, looking at that chart. But that's not all. You have to think about how you're going to plant and harvest the seed, how you're going to crush the seed, the tons per day. And you think about that cake output, because again, when you crush it to get the oil off, there's a lot of fibers and carbohydrates and other things left over. And so what are you going to do with that? Is that going to be animal feed, or what's going to be with that kind of cake that's left over? And then the oil that is pressed out, that's crushed out, how are you going to store it? When we're thinking about the plant and setup, we always need to think about the safety. Again, properly storing chemicals, ventilation of the space, your face shield, glasses, chemical breather mask, work boots. Again, we always need secondary containers that are larger than the container that we're using, chemical fire extinguishing, first aid kits, etc. Again, we need a heated and ventilated space, power, again, sparkless switch and pump motors, because again, the methanol is flammable. water for washing and testing, spill guards to handle each spill, again, 110% of the container. And then again, we have to heat it. So we're either going to heat it through solar, through electric, through a jacket heater. We have to think about how we're going to actually heat the process. So when we think about the basics, we need to stage and pre-measuring tank. We have the induction tank, where again, we have the methanol and the OH, the catalyst, which is usually an AOH. We have a reactor, which again, we're going to size based on the gallons per day, gallons per batch, again, large scale, small scale. We have to have some sort of settling tank for glycerol removal. We need to clean the biodiesel. And so we're either going to do that using a water wash or dry wash column. And then if it's water wash, then we have to dry the fuel after that. Again, the main consideration is often this methanol. How are you going to source it? How are you going to transport it? How are you going to store it, separate from the living? How are you going to, if you can recover it, again, we said about a third of it can be recovered. So you have to go through that process of trying to recover and reuse it as you can. And again, it is definitely the biggest danger of all. So again, this is a basic recipe of a home, I guess it's not brewing because it's not a biological process, a home titrator, a home chemical reactor chemist. So again, we're going to heat the oil. And then again, he's going to perform that titration so that he knows how much KOH or NOH that he need to add. Again, it can be potassium hydroxide or sodium hydroxide. We really are worried more about the OH. And then he does about 22% me by volume, which is a little high, but again, he wants to make sure he has plenty, and then he tries to recover the extra. He's going to mix and agitate for 2 hours. He's going to perform the 27-3-3-27 test. And that basically is looking to make sure that the reaction has taken place. And so it's a titration mix, a test to make sure you have had the reaction go to completion. And then he's going to have a settling tank for this recovery of this methanol. Then he's going to remove the glycerol, again, this gooey byproduct, and then he's going to wash, and then he's going to dry. And so after you wash, you make sure there's no soap left over, and then you're going to dry it and make sure there's no water left over. So in terms of waste management, if you are washing, doing a wet wash process, then you need to think about that soapy water and what we're going to do with it, how we're going to manage it. If we are dry washing, and then we have perlite. Again, that dry washing, though, that perlite needs to be either dried, regenerated, or we need new perlite over time. Again, the old methanol, if we are using methanol recovery, how are we going to store it? Glycerol, as he says, again, this is Matt McShane, who does this home process, is that everlasting soap supply. You can use it in anaerobic digestion, but it often is used for soaps. Again, any used fryer oil that's not used, if you have kind of parts in it, or, because sometimes with the used fryer oil, you don't get only fryer oil, or maybe some chunks of French fries and other things. So you either need to compost that, digest that, or send it to a rendering company. And again, if you are having a cake that's left over, if you're doing seed production, you can compost that, that extra plant material, or you can use that for feed. Biodiesel Challenges, this is again for home chemistry, is the cold weather operations, producing enough feedstock oil to replace a large portion of the petroleum that you're using. And then again, kind of, optimizing your engine and making sure it runs well. So again, if we think of the environmental issues with biodiesel, and you think about the carbon cycle, again, we talked about this for ethanol as well, but the idea that, the plants through photosynthesis take in the CO2, then when you're using the biodiesel and you're burning that biodiesel, that CO2 is again the same CO2 that's taken up in the plant in that plant's lifetime. We look at relative greenhouse gases, again, looking at gasoline, petroleum natural gas, compressed natural gas, liquefied petroleum gas, biodiesel or diesel, ethanol 85%, B20, hybrid, diesel hybrid, electric, and then again, depending on where you're getting your electricity from, and then B100. So again, in terms of the study, it had one of the lowest relative greenhouse gas emissions. Again, it really depends on where you're getting your, what you're including in your analysis. This is a different analysis, and where you're getting your oil from, because that's going to have a big difference. So if you're getting your oil from cooking oil and tallow, then again, that that cooking oil or the leftover animal fat that's there has a much lower emissions factor than if you're getting it from, soy from Brazil, for example, because the idea with soy in Brazil is that there may be some land use change. And so the greenhouse gases emissions associated with that land use change, less so in the US. Again, depending on the studies, they had different amounts of even oil seed, rapeseed oil. Depends on where you're growing it and what the land use change implications of that are. And then again, your palm oil, because even though there's land use change associated with it, and in this analysis, at least with CO2 emissions, was a little bit lower because you get so much more oil from it compared to coal, gasoline, diesel, and natural gas. And then if we think about the carbon of that CO2 emissions that we do have, again, a lot of those emissions are going to be based on the production. If we're doing soybeans for here, so there's so much soybeans, so much greenhouse gases just associated with farming those soybeans, fertilizers and soybeans and harvesting. The drying and the storage is a little bit, the transport to the port. But that again, if we use that co-product, because we're pressing the oil, we're getting the oil out of it, but then we have that feed. And so then that feed can go into kind of a negative emissions because we're using that for two different places. We're using the production is being used both for soy meal as well as for the biodiesel. Again, that processing to the oil, the transporting, the esterification process, again, a lot of that is the methanol right there, because methanol is usually produced from non-renewable resources. And so then here is our total. But again, it's not just CO2. So if we look at CO2 emissions, again, B100 is much less than diesel, for example, in this study as well, looking at 100% being diesel. And then we see that the CO2 emissions from B100 are about 25% of that of diesel. Again, usually this is like, mutations from cancer causing mutations that can happen, again, being less than 20% of that. PAH is again less than 20%. Sulfates are closer to diesel, about 80% of the emissions of sulfates from diesel. NOx is a little bit more, but again, that depends on what your feedstock is. But again, they are nitrogen containing. So when you burn it, there is NOx that is released, particulate matter being about a little less than 80%, carbon monoxide being much lower. That's particulate matter, excuse me. Here is the 100% biodiesel marks. I'm so sorry. So when we look at some of these with sulfates with 100%, we have much less. I'm sorry. Much less here with NOx, again, much less being 100%. We're getting some NOx if we have 20%. Particulate matter with 100% again is quite low. Here's our carbon monoxide, and then our unburned hydrocarbons. So again, much lower with our 100% biodiesel compared to 100% being our diesel. So this assessment actually looked at indirectly included emissions from land use changes, and looked at several different types of advanced biofuels, both that are done at the demonstration scale as well as the commercial scale. And so what they found is, for example, IGO biodiesel at the using algae for biodiesel, it really depended on the percent emission reductions compared to fossil fuels all over the map at the pilot scale. Cellulosic ethanol, again, they're saying that with cellulosic ethanol, we can get a reduction, at least for the demonstration scale. Again, with biodiesel, the same thing, with biogas. And then if we look at the commercial scale, again, with sugarcane ethanol, we do get a reduction compared to emissions with fossil fuels. Sugar beet ethanol is a little bit lower. Wheat-based ethanol and corn-based ethanol, it depends. So we do get some studies, and depending on the practices, that may not be as great. And again, these are going to be your gasoline. If we look at rapeseed and palm oil, again, same thing. We are seeing these in commercial reductions, and we are seeing reductions in greenhouse gases in this analysis of about an average of about 60–50%, depending on the study. And then again, biogas, the same thing, which with a wide range. I mean, some of these are as low as 20%, but it's going as high as 80%. And again, we need to think about, if we're thinking about density, if we look at the megajoules per liter, we can see that, again, gasoline is fairly dense, 35 megajoules per liter, ethanol being much less dense than that, less than 25. And then if we think about sorry, if we think about butanol, we're here. But if we think about diesel, it's again the most dense of all, and 100% biodiesel is much more closer to its kind of fossil fuel counterpart than ethanol is compared to its gasoline counterpart. So again, it's actually more dense in terms of megajoules per liter than gasoline is. And we also need to think about the engine efficiency. So our gasoline engines around 30%, our diesel engines around 39 to 40%, 45%, which is why large scale, why our trucking industry mainly uses diesel engines. And the electric engine being about 90%. So again, when that biodiesel is in there, we're still seeing that 39 to 45%. So it's much more efficient if once we put it into our biodiesel engine. And again, depending on the energy ratio outputs, it really depends on what study you're looking at. But according to our reading in Jones, soy biodiesel is about 4.5 energy units out for every 1 energy unit you put in, compared to corn bioethanol, which is about 1.6 units of energy out for every 1 unit of energy that you put in. All right, thank you very much.